Assalamualaikum and hi everyone. So in the session of interaction of radiation with matter, I'm going to briefly explain about the attenuation process that happened when the radiation impact the patient body. So firstly, what you need to know that the meaning of attenuation itself is the reduction number of photon beam when passed through the materials or the matter. So the interaction that happened that causing the reduction of X-ray, it can be from absorption, scattering, and also absorption plus scattering. So if you look at this diagram, the X-ray coming from the X-ray tube, there are three different processes happen. Firstly, absorption. X-ray pass through the patient body and it is absorbed within the human tissue. And you look at here, there is no X-ray coming out from the patient body and reach the films. So this is the absorption process. The second process is that X-ray transmission. X-ray pass through the patient body without any interaction and it reach the films. And thirdly is scattering and plus absorption. X-ray pass through the patient body, interact with the matter. A part of the energy was absorbed by the materials and a part of it is scattered and reach the films. Okay, that's the brief general idea of attenuation process. So now we are going to go to interaction radiation with the matter. There are two interactions of radiation with human body. Firstly, interaction of photon, which is X-ray or gamma ray with the human tissue, and another one is interaction of electron with the human tissue. So firstly, I'm going to explain about interaction photon with the matter. The photon here means that either it is X-ray or gamma ray. So before we go details, I'm going to explain the interaction for two different applications, which are diagnostic imaging and another one is for radiotherapy. So different application, the interaction that happens within the human body is different. We're going to go for that a bit later. So firstly, let's go to diagnostic imaging. What are the importance of diagnostic imaging? So when we do any radiation to the patient, what we want outcome from that particular application is that we want to produce a high quality image of radiograph or good contrast within the different tissues. So you look at this radiograph image of chest X-ray, lung appears dark region where the bone appears white region. So the differences between dark and white in one films is a differential absorption. Why this kind of films appear or occur? That is due to different interaction happen within the patient body during the irradiation. So bear in mind that in one single exposure, there are various of interaction happen within the body. It's not that one exposure, one type of interaction. One exposure, there might be two or three different interaction. So what we want from this diagnostic imaging is actually a good quality image so that we can get different contrast between the human tissue. If let's say there is no interaction, what happened within this film? If all the photon, there is no absorption and scattering, all the photon was transmitted, then this film will appear black. There is no contrast between, or there is no differentiation between soft tissue with the bone and the rest. If let's say all of the beam was attenuated or has been absorbed, so there is no X-ray transmitted through the film, then this image will appear bright or very white. Okay, we cannot see any of the organs inside the patient body. So the purpose is to diagnose the disease. So they are using, for diagnostic imaging, we are using low energy of X-ray or gamma ray. So the application is general X-ray, dental, mammogram, CT scan, and also fluoroscopy. So this is for application of X-ray. Whereas for radiotherapy, the differences between these two, this is using low energy X-ray, and this one is using high energy X-ray, usually up to from 4 MeV up to 21 MeV of energy. So the purpose of radiotherapy, instead of to get good quality of image, the radiotherapy is used to kill the tumor cells or to kill the cancer cells. And if you look at here, the region, the color region here, is mean the beam. The radiation beam is only confined to a small area of the cancer cell. Whereas for diagnostic imaging, we open up the radiation beam to cover whole of the organs of what we want to image. So this one, we only confine the radiation towards only at the cancer cell. Why? Because this is using high energy of X-ray or gamma ray. So we want to make sure that the normal tissue surrounding the cancer cell is secure or safe. Okay, so you already understand about the differences between diagnostic imaging and the radiotherapy. So different application, different interaction will occur. It depends on the energy of the radiation. So low energy radiation, X-ray or gamma ray, the interaction that can happen within single exposure, this can be scattering, coherent scattering, photoelectric effect, and Compton effect. Whereby for radiotherapy, the interaction is from Compton effect, pair production, another one is photodisintegration. So let's go to coherent scattering. The first thing that we need to know, the differences between this interaction, firstly, the energy of the radiation. For coherent scattering, the energy from the photon beam is very low, which is less than 10 keV. So when low energy of X-ray passes through the matter, it doesn't transfer its energy. It just causes the atom to just vibrate, just to have a vibration, and then it will leave the atoms with a different direction from its original. So it has a scattering. If you look at here, this is incident, no energy loss, and then it was travel with different direction. So for this coherent scattering, it is not important in the diagnostic range. Now let's go to photoelectric effect. The photoelectric effect is occur at a low energy of photon beam, less than 100 kVp or keV. So most likely less than 60 kVp, the photoelectric effect is dominant. So the interaction of the attenuation of photoelectric effect is by absorption. For this one is by scattering. Photoelectric effect is by absorption only, which means that when the radiation travels through the patient body, it transfers all of its energy towards the innermost orbitals of electron. So the interaction at that point is absorption. It is very important in diagnostic because we can get this kind of image, because this image is coming from absorption, transmission, and also from the scattering. It causes ionization of the atoms. Why? When the inner orbital's electron absorb that energy, it gains a lot of energy, and it becomes ejected out from the atoms, leaving a hole inside that orbital shell. And then the electron that come from outer shell will fill in the holes, while the outer shell jumps into the holes. It will transfer its energy, or it will convert its energy, becoming the characteristic X-ray. So the atoms will be ionized. It is contribute to image contrast, something like this. The dependence of photoelectric effect depends on atomic number. So greater atomic number will produce much more absorption. As example, if you look at this image, the lung has low atomic number. Okay, lung has a low atomic number or low density, while bones has higher or greater atomic number compared to lungs tissue. So because of bone has greater atomic number, it will absorb more energy from the incoming photons compared to lung. That is why it will appear bright and the lung will appear black. Black means that, or dark means that more X-ray will be transmitted to the films. White means that more X-ray is being absorbed. Okay, so it is dominant at low energy, and the product of photoelectric effect is photoelectron, characteristic X-ray, and also the ionized of the atoms. Now let's go to the Compton effect. The Compton effect is dominant at higher energy. When the energy is greater than 60 kVp, it started to increase its probability of occurrence until at one point at high energy, like say 10 MeV, the probability will drop. Okay. So interaction or attenuation process happens for Compton effect is by absorption, and another one is scattering. How so? The incoming photon energy transfer a part of its energy to the outer orbital shell. Compared to here is inner, this is outer orbital shell. A part of energy is used to overcome the binding energy and causing this electron ejected out from the orbital shells, and a part of another energy is used to travel to incident onto another atoms, which we are going to look at in the interaction of electron with the metal electron. Okay, so it is not important in diagnostic. Why? Because it is contribute to two effects on diagnostic. Firstly, it contributes to higher dose to the patient, and another one, it contributes to poor contrast to the image due to that scattering photons. Okay. It also caused the ionization of atoms because the surveillance electron was ejected out from its atoms. Compared to the photoelectric effect, this Compton effect depends on the electron density. What is meant by electron density? It is amount or number of hydrogen within that particular organs. Okay, is dominant at high energy. So the product for Compton effect is that it recoil electron. Okay, later I'm going to touch more detail for photoelectron and recoil electron, because these two electrons are the one that are responsible to cause further ionization within the human body or within that selected area, which I'm going to cover later on here. So for Compton effect, one more thing that you need to know, it occurred in both diagnostic and also in therapy. But in diagnostic, it would be better if we can neglect the Compton effect. But of course, it also happened within the exposure. So it is most important, this interaction is important in therapy compared to diagnostic. So let's go to pair production. What is a pair production interaction? Firstly, the energy for pair production to happen is greater than 1.02 MeV. So the interaction of the photon is with the nucleus. So this photon will approach the nucleus due to the Coulombic interaction, Coulombic force. It produces another two ion pair, which is electron, and another one is positron. This positron will travel and incident with another electron and producing two identical photon beam. This interaction is known as annihilation. Okay. So what happened in this interaction? The photon lost all of its energy when it collides with the nucleus to produce beta and positron. Okay, each of these beta and positron beam having energy 0.511 MeV. So if we sum up two beams, it will become 1.02 MeV. That is why the threshold energy for this interaction to happen must be greater than 1.02 MeV. And this interaction can only be happen in the radiotherapy applications. Okay. What about the photodisintegration? The photodisintegration is only occur when the energy of the radiation is very large, which is around 7 to 15 MeV. And the interactions happen when the photons incident directly with the nucleus, and it causes the nuclear particle to be ejected out. It can be either neutron, proton, or even alpha particles. So this interaction also happen for the radiotherapy part.